Hi, this is Bogator from LangChain, and today I want to show you how we can build a data analyzing agent using LangGraph and Azure Container Apps dynamic sessions. So the agent we'll build will be able to query a SQL database and then write and run Python code to analyze the retrieved data. It'll be built on top of LangGraph and make use of the new Azure Container Apps dynamic sessions. Dynamic sessions is really the key feature we want to show off here. LLMs are great at a lot of things, but raw computation isn't one of them. Fortunately, LLMs are great at writing programmatic logic that, if executed, could perform the raw computations for the LLM. So if we had the ability to hook up our LLMs to fast and safe code interpreters, then we could unlock a lot of use cases. Fortunately, this is exactly what the Azure Container Apps dynamic sessions integration allows us to do. It is a reliable and safe code interpreter service provided by Azure Container Apps, now in preview, and it has a nice LangChain integration that makes it really easy to use with any LangChain and LangGraph agents that you build. And as a sneak preview of where we're going to get, in my case, I'm going to hook up my agent to a database of LangSmith traces. If you're not familiar, LangSmith is our observability and evaluation framework. And one of the key things it does is trace LLM applications, including things like the latency and token counts and inputs and outputs of different LLM calls. And so once I've hooked up my agent to a database of LangSmith traces, then I can start to ask it questions like, or make requests of it like, graph the average latency by model, and it's able to generate these nice plots for me, showing the different latencies for different models across the traces within my application. And the agent architecture we're going to use for this is actually pretty simple. We will use a tool calling model to be able to invoke two different tools, one for writing and executing SQL queries against our SQL database, and the other for writing and executing Python that is given access to our retrieved data and then can perform computations on it. So let's see how we can actually put all of this together. First, we'll need to install all of the relevant dependencies, chiefly LangGraph and the new LangChain Azure Dynamic Sessions integration. Then we'll need to set up some credentials. In this case, we'll use Azure OpenAI for our model. We'll use Azure Postgres for our DB, and of course, Azure Container Apps Dynamic Sessions for code execution. The links in the notebook should show you how to set up all of those, and the LangGraph architecture we're going to show here should actually generalize to any LLM that has tool calling abilities and to any SQL database. Now we can set up all of our credentials for these various services. So first, we'll set up Azure OpenAI. And then our dynamic sessions. And lastly, our SQL database. One important thing to remember whenever you are hooking up a model to a SQL database is that there's inherent risks in executing model-generated SQL, and it's really important that you scope your connection permissions as narrowly as possible given your application. So in this case, we only need our agent to be able to read from our SQL databases. So we should scope the connection permissions accordingly. Once we've set up all our credentials, we can import all of the relevant classes and methods and actually instantiate our SQL database, our Azure OpenAI model, and our sessions code interpreting tool. Now we can actually define our LangGraph agent. So the core elements of any agent are the state, nodes, and edges. So nodes are where the agent actually performs various functionality. State is what is passed through all of the nodes. So the input to every node is the current agent state, and the output of every node should be an update to that state. And then edges defines the flow of our agent from one node to the next. In our case, our agent state will be simple. It'll just be a sequence of messages. And the only custom message we'll need to add is something we'll call raw tool message. Our tools will be creating outputs like data frames, and in the case of our code interpreter, sometimes images. And we want these things to be part of our agent state so that they can be accessed by future nodes, but we don't want these to be part of any message contents because we don't want data frames and images to be sent back to our model in future model invocations. So we'll simply add a new attribute to our tool message. We'll call it raw for raw tool outputs. And this will allow us to add arbitrary additional tool outputs to our tool messages so that future nodes can access the tool outputs, the full tool outputs of past node executions. So now we can define the actual nodes of our LangGraph agent. As a reminder, we will have 3 main nodes. One will be for actually calling our model, and then 2 for executing the tools that our model might invoke. One for the SQL tool, one for the Python tool. So in the case of the model node, again, we'll be using tool calling APIs to make sure that our model is correctly invoking the tools that we wanted to have access to. And tool or function calling, in case you're not familiar, is a specific type of chat model API that allows you to pass in tool schemas when you're calling your model and have it generate inputs to whatever tools you've passed schemas in for. Crucially, the tool calling models don't actually call the tools, they just generate inputs to the tools. It's up to the application to actually then take those inputs and pass them through to the tool. So in our case, we will have 2 tool schemas that we'll be passing to our model. One we'll call create df from SQL, and the other we'll call Python shell. So the create def from SQL will be for querying our SQL database and generating pandas data frames from that. And so the key attribute of this tool schema will be the select query attribute, which should just be a SQL select statement that our model generates to get relevant data from our SQL database. And then the other 2 attributes will be df columns and df name. So once we extract data from our SQL database, we'll convert it into pandas data frames that have the corresponding variable name and the column names that the model generates. And then our Python shell tool is really simple. It just has one attribute, code, which should be Python code that we want our code interpreter to execute. The other part of our model calling node is there will be a simple prompt. The prompt will have a system message, and then we'll pass in whatever messages are in our state to the model as well. The system prompt will have a little bit of positive encouragement, telling the model that it's great at SQL and Python, and then also this db.table info information. So if we look at what this looks like in this case, like I said, the database I've connected my agent to has Langsmith traces in it. And so if we look at db.tableinfo, it should tell us a bit about the table schemas that are in my database and have some example rows from my database. And this is really important because if we want our model to be generating sensical SQL queries, then it needs to understand what types of tables are in the SQL database that it's being given access to. So this information should all be in my prompt that is being sent in every model call. And then the rest of what's happening in the actual node is we'll chain together our prompt with our LLM. We'll make sure to bind our tool schemas to our LLM so that it knows how to invoke the different tools that it can. And then we just pass through all of the messages in the state when we invoke our simple prompt LLM chain, and this invocation will generate an AI message, and we simply add that AI message to our message state. So after this node is called, our agent state should have one extra message in it, which is an AI message. After our model calling node will be our SQL executing node. So this node will simply check the last message in our agent state. Since this node always will set up to always be called after the model calling node, we know that the last message is always the AI message, the latest AI message, and it'll check for any tool calls to the create df from SQL tool. If those exist, it will run whatever SQL query was generated and get back the results. These will be a list of dictionaries, and it will store those results as a pandas data frame. It'll create the data frame with whatever columns the tool call generated. So the model gets to decide what the data frame column names are, and we will also store the name that the model generated to give the data frame variable. This will become useful in our Python code execution step. And then we just append a tool message to our agent state. The actual contents of this tool message will simply say that a pandas data frame with a given variable name and with certain columns was generated. And then in the raw attribute of our tool message, we'll store the actual pandas data frame so that it can be accessed by the Python code execution step without actually being sent to the model in future model invocations. And so once we have called our model and executed any SQL queries generated by the model, the last step is to execute any Python code that the model has written. And the way this will work is, again, we will find the latest AI message, which will include any Python shell tool calls on it, and we'll find any Python shell tool calls. And once we found one, we'll take the code the model has generated, and we will use our code interpreter and actually execute that code. Now, there's a few extra things that we have to do here. So we're having our model generate the code, assuming that it has access to certain pandas data frames. Now, the model will know what data frames it has access to because it'll have come up with the data frame variable names when it actually generated the SQL query. So the SQL query will have the SQL tool calls will have the SQL query. It'll have the data frame variable name and the data frame columns. So the model will know exactly what it called every data frame that it generated via a SQL query. It'll write code assuming it has access to that data frame variable. But of course, the code interpreter isn't local. By default, it doesn't have access to any of the data that we have in our backend. So we need to somehow upload the data frames we generated with our SQL queries to our code interpreter. Fortunately, this is possible with the dynamic sessions code interpreter. There is a nice upload file functionality that they provide. So what we're going to do is, before we call any of the code generated by our model, we're going to upload our data frames to our code interpreter. The way we're going to do this is we're going to go through our agent state and find any tool messages, which were the output of the create df from SQL tool. And we're going to take all of the data frames that were generated by those SQL queries and upload them as CSV files to our code interpreter. And then we're going to write some simple Python code for loading those CSV files as pandas data frames with the names that the model thinks it gave those variables. And then what we're going to do is we're going to take that code for instantiating those pandas data frames with the expected variable names and prefix all of our model generated code with that. So when our model writes code like df1 dot sum columns a, b, c, we're going to add before that import pandas df1 equals pd.read csv, whatever the correct CSV path is within the code interpreter. And then the model generated code will actually have access to something called df1, or whatever variable name the model previously decided to assign to that data frame. Once we execute our code interpreter with the model generated code, we will get back a few different types of results. So if we look at what the dynamic sessions code interpreter returns with a simple example, it has a few things in it. It has standard out for any standard output generated by the execution of the code, standard error if errors were generated, and result for whatever the actual results of the code was. In this case, since we just have a print statement, the only thing that's populated is standard out. But in general, standard out and result can both be not just text, but also richer outputs like images, base64 encoded images. So what we're going to do is we're going to take our code interpreter output, and we'll need to parse it a little bit before we can create a tool message out of it. Specifically, we want to make sure that if there's something like images in our code interpreter results, we display those images, but we don't actually include them in the contents that we send back to the model in future model calls. And so what we're going to do is we'll simply remove any images that are returned as part of our code interpreter result. And since we're in a notebook, we can just display them. But if this were being run in a different environment, we could pass them along some other way. And those are what the tool message outputs will be of the Python execution node. And those will get appended to our agent state. So now that we've defined all of our main nodes, we can define the edges, which will connect our nodes. Again, this will be pretty simple. We will have a call model node, which will be the entry point to our graph. We'll have an edge from our SQL execution node to our Python execution node, and from our Python execution back to making a model call. And then every time we call the model, we'll have a conditional edge. Basically, if our model decides to call any tools, then we will execute the SQL and Python nodes and go back to the model. And then if our model ever doesn't have any tool calls, that means that the model is ready to respond to the user, and we will end the agent run. And the latest AI message will be returned to the user. So that's our agent. Now we're ready to try it out. Again, in the examples that we're going to see here, the results and queries will be related to the specific database that I've hooked up my model to. Once you hook up your own database, you should ask it questions and hopefully get results related to the data that you've given it. So we can try running our, let's actually run these cells. And now we can try actually running our application. So the first thing will be simple, graph the average latency by model. We can see what that looks like. And after a few seconds, we get this nice graph. And a nice message from the model. And actually, in this case, doesn't understand that we can visualize the outputs that it's generating. And if we're curious to see what the trace looks like for this model call, For this agent call, we can see that under the hood, we've called our model 3 times. So the first time we call the model, it has access to these specific tools. Here's the system prompt that we're passing in every time. And here's our request. And here's the first thing that the model generated, which is it called the createDF from SQL tool, and it wrote the following select statement and generated a pandas data frame that I called df average latency. And then when we got to the execute SQL query node, it actually ran that, and we see that our tool generated this simple content, which we know isn't the full content of what the tool actually generated, but this is what we're sending back to the model. The execute Python didn't have any output because there weren't any Python tool calls in this first cycle. Then we get back to calling our model again, and this time we're passing in the our system message, the human input, the first generated AI message which had the tool call, and the output of that tool call. And this time the model calls the Python shell tool instead of the SQL query tool. And notice that it writes code assuming it has access to this df average latency variable. And so when we next execute the Python code, we know that what we're actually doing before running this Python code in our code interpreter is prefixing it with a pandas import statement, which actually loads df average latency as a variable in this code. And in this case, our code interpreter won't be showing any results in the tool message, but that's because the main result was an image, which we removed from the tool result and displayed in our notebook. And then we can see that in our last model call, which now has all of the messages in our agent state up to this point, it finishes with simply returning a message with no tool calls. And that's when our agent knows to stop the cycle. So now let's try a slightly more complex agent call, and we'll ask something that's slightly higher level and more fuzzy about exactly what we're asking the model to do. And we'll say, what's the relationship between latency and input tokens? Notice that we're not telling it that it should graph something, whether to explicitly compute correlation or some other dependency statistic between latency and input tokens. We're just stating something high level. Let's see what it generates and see what the model is able to come up with for that. And again, our agent is able to come up with a pretty reasonable answer. It graphs the relationship between prompt tokens and latency, specifically for the Gemini Pro model, and then it also computes correlations between prompt and latency, controlling for the different models. And we can see that there actually is a pretty big difference between the correlations, with Anthropic seeming to be latency seeming to be much more dependent on prompt token length than some of the other models. Now we can try continue our conversation. We could ask, what about latency versus output tokens? See what that generates. And then maybe while we're at it, one last even higher level question: what's the better explanatory variable for latency, input or output tokens? And let's see what it generates for those two questions. We can see that for the first question of latency versus output tokens, our model generates actually quite a nice graph showing the different latencies color-coded by model and already computing and displaying some correlation lines. And it computes the correlations, controlling for the different models, and gives us a little analysis of which models show the highest correlations between output tokens and latencies. And it does seem like in general, output tokens is a better explanatory variable for latency. So then when we ask this final question, we can see that our model comes to a similar conclusion, computing the correlation between input tokens and latency and output tokens and latency, and concluding that output tokens has a higher explanatory, has more explanatory power. So there's our data analyst agent. So just to recap, we built our agent such that it could execute SQL queries against the SQL database and then take whatever information it retrieved from the database and upload it as CSVs to the Azure Container Apps Dynamic Sessions code interpreter, and then actually write code to interface to analyze those CSV files. And we made it so that our agent could actually return rich results like displaying images and such. So that covers the data analyst example. There's links in the videos to this notebook and to all of the relevant documentation. And we're really excited about the Dynamic Sessions tool and can't wait to see what others think to build with it.